Good morning, students. In the previous class, we have discussed the theory of interference and the conditions for the constructive interference and the destructive interference, which means the condition for the bright bands to be formed and the conditions for the dark bands to be formed, both in terms of phase difference as well as path difference. In continuation with that, here it is a single slit, rectangular single slit of a large width in a cardboard. A monochromatic light, that is a sodium source, gives out yellow color light. Yellow color light is made to incident on the single slit. The wavelength of yellow color light is 589 nanometer or 5890 angstrom units. That yellow color light gets distributed on the screen uniformly. Light intensity is uniform on the screen. So the light transmitted through S1 spreads out over the screen uniformly. There is no modification in the intensity of light. So here the intensity of a light coming from the source is say I naught. The intensity of light transmitted through the slit is also I naught. The intensity of a light on the screen is placed at a suitable distance from the single slit is also I naught. So there is no modification in the intensity of a light. If a single slit having a large width, the light transmitted through this gets distributed uniformly. If you consider two sources of the same kind, suppose the intensity is say I naught for one source, I naught for the other source, then also if the slit, then also the intensity of a light on the screen is 2 I naught. The intensity is algebraic sum of intensities of the sources from which the light gets spread over the screen. If you go for 3 sources, 4 sources, then the intensity of light here increases. It becomes 3 I naught, 4 I naught for 4 sources. So there is no modification in the intensity of light. Whereas in a Young's double slit experiment, a single slit S is illuminated with the same monochromatic source, sodium source, with wavelength 589 nanometer. The intensity of light is I naught. So the wavefront which reaches simultaneously to the both S1 and S2, it is divided into two parts. Divided wavefront have the intensity I naught and I naught. Since the width of both the slits is the same, the intensity of light that gets transmitted through both S1 and S2 is the same. The amplitudes of the waves are also same. So speed of the wave, frequency of the wave, amplitudes are same, traveling nearly in the same direction. Then the intensities of the light coming from both S1 and S2 is same, that is I naught. The waves arrive at the bright fringe constructively. Crust falls over a crust or a trough falls over a trough throughout the experiment. Since the sources being coherent, the phase relationship doesn't change. At the center of the screen, the intensity of light need to be 2 I naught, but instead of 2 I naught, the bright fringe intensity is 4 I naught. That we'll discuss it later, the theoretical part. The waves are arriving at a point where the dark band is formed. Destructive interference takes place, crust falling over a trough or a trough falling over a crust cancels each other's effect. The amplitudes being the same, the amplitudes of the individual being wave being the same, they cancel each other's effect. Resultant amplitude is 0. The intensity is also 0. But the light is reaching to this point from both S1 and S2, light adding to light produce darkness. But according to law of conservation of energy, energy neither being created nor destroyed. Here I naught plus I naught, that intensity of light is not going to get destroyed, but that energy lost in the dark band appears in the bright band. That's why the intensity of a bright band is a 4 I naught, not just 2 I naught as in the first case. Here if you have two sources, the intensity will be 2 I naught. If three sources are there, the intensity will be 3 I naught. If width of the slits are too large. But here what happens, there will be a modification in the intensity of a light at various points on the screen due to redistribution of a light energy. Energy lost in the dark band appears in the bright band. So at the bright band, the intensity is not just 2 I naught, it is a 4 I naught. The 2 I naught lost in the dark band appears in the bright band. That's why the bright fringe intensity is 4 I naught and dark fringe intensity is 0. Suppose if the intensities of light from S1 and S2 are I1 and I2, the amplitudes A and B, amplitudes not being same, then the point where the destructive interference takes place, then the dark band is not completely dark. Some part of light will be there on the screen where the destructive interference takes place. There will not be good contrast between the bright and dark bands if amplitudes are different. If amplitudes are same, then the dark band is completely dark, intensity is 0, then there will be a good contrast between the bright bands and dark bands. So there are necessary conditions to obtain this interference pattern. Namely, we need first two coherent sources. S1 and S2 must be coherent sources. The waves emitted from these two coherent sources, the phase relationship must remain constant, and the width of the slit should be very small, that is a fraction of a millimeter. The width of the slits, say let us take 0.5 millimeter. The distance of separation between the two slits, that is a small d, is the distance of separation between the two slits. It is of the order of millimeter, say 2 3 millimeters. Say let us take 3 millimeters. And the distance of the screen from the plane of the two slits must be of the order of 1.5 meter. If these are all the cases, source must be a monochromatic source. So here yellow color bright bands which are separated by dark spaces, that is the interference pattern what we get on the screen. So these are the necessary conditions to get the interference pattern in the laboratory. So once again I will recall that source must be monochromatic source, and a single slit, yes, should be illuminated with a monochromatic light, and two more slits made in the cardboard S1 and S2 of a small width of the order of 0.5 millimeter, separated by a small distance, say 2-3 millimeters, right, placed at equidistant from a single slit S, and a screen must be placed at a suitable distance from the plane of the two slits. The distance capital D must be of the order of 1.5 meter. If these conditions satisfy, then there will be an interference pattern on the screen, or we get interference pattern on the screen consisting of alternate bright and dark bands. So the waves superpose each here, and either constructively or destructively. Hence there is a modification in the intensity of a light due to redistribution of light, that is energy lost in the dark band appears in the bright band, is called phenomena of interference. So further we discuss in detail the intensities of a bright band and dark bands. If amplitudes are different, if amplitudes are same, then the ratio of brightness of the bright band to the brightness of the dark band, the ratios of the intensity of a light coming from the two sources, so and so forth. Note number 1, intensity of source S1 is I1, which is directly proportional to square of the amplitude, or I1 equals to K square, where K is a proportionality constant. Intensity of source S2 is I2, which is directly proportional to square of the amplitude. As width of both the slits are different, that's why the amplitudes are different, intensities are also different. If the width of both the slits are same, then the intensity of both the sources are same, amplitudes are also same. Here we are considering the intensities are different, the widths of the slits S1 and S2 are different, thereby the amplitudes are also different. Then a ratio of intensity of a light from the two individual sources, I1 by I2. Intensity of light coming from source S1, intensity of light coming from source S2, I1 by I2 is equals to K held cancel, therefore it is A square by B square. Further, we have deduced an equation for the resultant amplitude of a resultant wave, that is R equals to under root A square plus B square plus 2AB cos pi. This third term is the interference term that determines the intensity of the bright band and dark band, or R square equals to A square plus B square plus 2AB cos pi. Then a resultant intensity of light at a point on the screen where the waves from S1 and S2 superpose is given by this particular relation. Resultant intensity IR, this a point on the screen, the intensity of light called a resultant intensity is equals to I1. I1 is proportional to A square, that's why we are writing here I1. Here also the K held cancel. For B square we are writing it as I2. 2 for A root I1, for B root I2, that's why root under root I1 into I2 into cos pi. The root is only for I1 and I2, not for cos pi. For a constructive interference, bright fringe to be formed at that point where the two waves superpose, the resultant amplitude R must take maximum value, R equals to R maximum. This is possible if cos pi is 1. Then equation 1 becomes, this equation cos pi is 1, then we get A square plus B square plus 2AB, which is nothing but A plus B whole square. And if you write R maximum equals to, R maximum square is A plus B whole square, R maximum is just A plus B. Since the phase difference is integral multiple of 2 pi or even multiple of pi, 2 pi, 4 pi, 6 pi, 8 pi, even multiple of pi. For a destructive interference, for a dark fringe at a point on the screen where the two waves superpose, R must take minimum value, R equals to R minimum. That is only possible if cos pi is minus 1. Then that equation for resultant amplitude becomes R minimum square is A square plus B square minus 2AB, which is A minus B whole square, or R minimum equals to A minus B, since the phase difference is odd multiple of pi. 1 pi, 3 pi, 5 pi, 7 pi, odd multiple of pi is the phase difference between the waves arriving at a point, then the resultant amplitude is minimum, which is the difference between the amplitudes of individual waves. Then a ratio of maximum intensity to minimum intensity of the interference fringes. So on the screen we will be having alternate bright and dark band. Intensity of a bright band divided by intensity of dark band is equals to R maximum square by R minimum square. R maximum is A plus B whole square. R minimum is A minus B whole square. I1 by I2 is the ratios of intensity of light coming from the sources S1 and S2, whereas the I maxima, I minima are the intensity of a bright band to the intensity of dark band. It is equals to the ratio of A plus B whole square divided by A minus B whole square. If light waves from S1 and S2 have same amplitude, that is width of the slits are same, then the amplitudes of the waves coming from both S1 and S2 are same, A equals to B, then intensities of light from S1 and S2 are same, that's why I1 equals to I2 equals to I0. Then resultant amplitude becomes A square plus 2A square cos pi. A square plus A square is a 2A square, taking it common, 2A square 1 plus cos pi. Or R equals to under root 2A square 1 plus cos pi can be written as a 2 cos square pi by 2. So 2 into 2 4A square cos square pi by 2. So resultant amplitude is 2A cos pi by 2, or R square equals to 4A square cos square pi by 2. Then a resultant intensity, resultant amplitude is R square is 4A square cos square pi by 2. Resultant intensity is directly proportional to resultant amplitude. Then the intensity of the individual sources I0 is directly proportional to A square. So here R square is replaced with IR, A square is replaced with I0. So then resultant intensity IR equals to 4 I0 cos square pi by 2. So this is equation 2. This equation 2 can be made used to calculate the resultant intensity for any arbitrary phase difference between the waves arriving at a point on the screen, the sources having the same amplitude and same intensity of light. Further, for a constructive interference bright fringe to be formed, the R maximum is A plus B. When A equals to B, then it is 2A, we write. And I maximum equals to K R square maximum, K 4A square, we can write, K held cancel, so it is 4 I0, since I0 is directly proportional to A square. For destructive interference, dark fringes to be formed, the resultant amplitude should take a minimum value, that is R minimum is A minus B. A equals to B is the condition, so B also we are taking it as A minus A is 0, so I minimum is directly proportional to square of the R minimum, which is equals to 0. Further, if the two sources are incoherent, independent bulbs, if two independent bulbs are made use, then a resultant intensity of a light at a point where the waves superpose each other is given by, in an angular bracket, resultant intensity IR equals to 4 I0 cos square pi by 2 between angular bracket. So if sources are incoherent, as we have discussed earlier, the light gets distributed uniformly over the entire screen. At a given point, there will be both constructive interference as well as destructive interference. So rapidly it will be taking place, since the speed of light being enormous, our eyes cannot detect that constructive interference and destructive interference taking place at a point on the screen for two independent sources. For us, the light appears to be distributed uniformly. The resultant intensity IR equals to 4 I naught. The average of cos square pi by 2 is 1 by 2. So here 4 divided by 2 is 2 I naught. The two independent sources, if their light is made to pass through a single slit of a large width, then the light appears to be distributed uniformly. At any point on the screen, the intensity of light is just the algebraic sum of intensities of both the sources, that is 2 I naught. Since the average of cos square pi by 2 amounts to 1 by 2, the average of quantity between angular brackets, that is cos square pi by 2, becomes 1 by 2. That's why the resultant intensity at a point on the screen for the two independent sources is just 2 I naught. Hence, the interference pattern is not obtained as the phase relationship between the interfering waves changes rapidly. 10 to the power of minus 10 second, the phase relationship changes. The time interval for the change in phase relationship is of the order of 10 to the power of minus 10, which is very small. In 1 second, so many number of times the phase relationship between the waves at a point on the screen changes. Hence our eyes cannot detect. The light appears to be distributed uniformly. The light appears to be distributed uniformly. Further, the path difference, the waves coming from both S1 and S2 at some point other than the center of the screen, definitely there will be a path difference. That path difference cannot be in a centimeter, meter, or so it is of the order of wavelength of light. The path difference will be of the wavelength of light. So delta is path difference. Path difference is denoted by delta. Delta path difference is a lambda. Then the phase difference will be 2 pi. For a path difference of 1 lambda, the phase difference will be 2 pi. Thus, path difference delta you can calculate if you know the phase difference pi. The relation is like this. Path difference delta equals to lambda by 2 pi into phase difference, whereas the phase difference pi equals to 2 pi by lambda into path difference delta. For example, if a phase difference is a 5 pi, determine the path difference. Means pi is given, delta you are supposed to calculate. Pi is the phase difference, delta is the path difference. Therefore, path difference delta is lambda by 2 pi into phase difference pi. So, pi is 5 pi, lambda by 2 pi into 5 pi, it is 2.5 lambda. 1 lambda is 2 pi, 2 lambda 4 pi, and 1.5 lambda is 2.5 lambda is 5 pi. If a phase difference is 270 degree, determine path difference. Path difference delta equals to lambda by 2 pi into phase difference pi. But here phase difference is given in degrees, you have to express in terms of radian. Then 270 degree is the same as 3 pi by 2 radian. Lambda by 2 pi into 3 pi by 2, you will get 3 by 4 lambda or 0.75 lambda. So 270 degree is a 3 pi by 2 radian. In terms of path difference, it is a 3/4 of lambda. So in the next class we discuss the derivation of the expression for the fringe width. Fringe width is denoted by letter beta. The fringe width is the distance between the centers of two consecutive bright bands or dark bands. So this is the interference pattern what we get on the screen. Actually on the screen it is not possible. We have to keep a micrometer eyepiece. Through that micrometer eyepiece we happen to see the interference pattern. It is a microscopic phenomena, and these are the alternate these are